Okay, so I figured we'd just finish up chapter 8 with the gas laws. There's just one thing I wanted to get to that we didn't get to last week. And then we're going to start in on intermolecular forces. And there's a good connection between the two, as you'll see, because some of the things that we've been learning about gases are because they lack some of the forces that keep molecules together. And you'll see that the more forces that bring molecules together, the less and less they appear and have activity like gases. So I figured we would just finish off chapter 8, and then we move on to chapter 10. So let me see if I can remember how to do this. All right. So you remember this from last week. It's just basically a plot of how the faster and faster molecules go, we can see that they're smaller and smaller. And it's one way we can measure the actual molecular mass of a gas is to see how fast it moves. And so you can see that these are distributions of speed at a given temperature. And to imagine like what a distribution would look like, I mean, sort of one way I like to think about it is if like, let's say you go into a kindergarten class, like, 30 kids in it. Some of them are going to be like running around at full speed, hitting the wall and like running into each other. And other ones are going to be sort of, moving slowly between the different tables and playing with their friends. Some are just going to be like, sitting at a table, playing with something by themselves. And some of them are going to be asleep. And so there's going to be a distribution of the amount of energy each one of those kids has in that room. And it's never going to be the same. There's going to be a distribution. But the average speed can be plotted sort of like this. So some molecules will have very little movement. Some will have a lot, but most will be somewhere in the middle. And so we can see that if we plot the speed versus the temperature, but here speed versus the molecular mass, large molecules move generally slower than small ones do. That kind of makes sense. Like if you're throwing, like I mentioned, if you throw a basketball versus you throw a tennis ball, you're gonna be able to throw a tennis ball a hell of a lot farther than you can throw a basketball. It's because of the mass of it. So the same amount of force will project something smaller to go a lot further than something larger. What this leads to is a way of defining the molecular mass based on speed. And so that led us to yet another gas law, like we didn't have enough already. So the effusion is just how gas escapes through a small hole in a container into a vacuum. And if you just think of spray, like if you have like cooking spray, you press the nozzle, and in that instance, small particles of liquid come out, but it's a gas that's propelling them inside. Generally, like I think they use like propane or butane these days as a propellant. And so the law of diffusion that Graham came up with is that since we know that smaller molecules move faster than big ones, and we know that the relationship between mass and force depends on the square of the mass, that he noticed that the rate of effusion of a gas from a small hole into a vacuum is related to 1 over the square of its molecular mass. And so if you had 2 different gases escaping and you could time how long it took one to escape and the other, the relationship between the speed at which they escaped from that particular container would be related to how their the squares of their molecular mass were related. And this is how fusion actually works. And so when you're measuring this, you're not actually looking at individual molecules or anything. Hey, what you're looking for is a change in the pressure. So what you're doing is basically watching the pressure decrease over a particular amount of time. And that's related to the square of the molecular mass of that gas you're looking at. So let's see how that would work in real life. So if you have a mixture, say you had a mixture of two different gases in an apparatus, just like the one I showed you before, and you get a mixture of helium and methane, they're mixed together. And you notice that, oh, yes, question. Was there a question there? I'm having trouble hearing because the dogs are still playing. All right, so you got a mixture of helium and methane. And if it takes, and let's say you're watching the pressure go down, and it takes 7.55 minutes for a given volume of methane to effuse from the apparatus. How long will it take for that same volume of helium to effuse? So you think about it and you're looking at it and you remember that the rate is going to be dependent on the speed, of course. The faster they move, the faster they're going to effuse. And so if it's smaller, it's going to take a shorter amount of time to effuse from the apparatus. And it's related to the square of their molecular masses. The first thing you need to do is think, oh, what are the molecular masses of each one? And so you find the molecular masses of each one, methane and helium, take the square roots of them, and then see what the ratio is between the two, okay? So the molecular mass of methane is around 16 grams per mole. Molecular mass of helium is around 4 grams per mole. So you take the square root of each one, and you see that the relationship between the two is 2. So the square root of methane would be 16 down to 4. Helium would be 4 down to 2, 4 over 2. So the ratio is 2. And so we would imagine that the ratio of the effusion rate would be the same. And so if it takes 7.5 minutes for the methane to effuse, it would take about half that for the helium to diffuse. And so it's methods like this that allowed scientists to determine the molecular masses of a lot of gases. They would do a reaction, fill a container with gas. They would predict what the gas was based on the reaction. And then they would calculate what the molecular mass was based on how quickly that gas would then effuse from the container into a vacuum, and figure out what the mass was based on something like helium that they were able to calculate very precisely. So any questions about that? I mean, it's an old school method, but it shows you again how we use the gas laws to determine moles, volume, pressure, temperature, and we can use them to determine molecular mass as well. And that's going to be related to the recitation we're going to do this afternoon, where we connect the thermochemistry that we learned in the last chapter to the gas laws that we're learning now. So any questions about that? So quiet. I must be doing such a good job everyone understands. All right, so this is just basic diagram showing how gases diffuse. And what I really wanted to point out here is that it's these collisions right here that result in pressure, like we've mentioned that before. Gas molecules bumping into each other, bouncing off each other, doesn't contribute to pressure. It's only when they hit the wall. So they can be moving, and we don't really notice they're there until they hit the sides of the wall. And as they diffuse, they should go from an area of higher pressure to one of lower pressure. And then we measure the pressure decreasing. And that's how we measure the rate of diffusion. Just quickly, this is just what we would say this is the composition of air at sea level. And just like any other mixture, we would say that this is a solution. It's a solution of gases rather than solids and liquids. It's a solution of gases. And so the solvent would be the one that's there in the highest concentration, and that would be nitrogen. I think we all knew that. It's around 78%. Oxygen is next. One thing that may surprise you, and it surprised me, is that there's so much argon, but 1% of the air we breathe is argon. But I figured it was. Then you can see that it just goes way, way, way down as we get these molecules that are there in like really, really, really low concentrations. Like, carbon monoxide, good thing there's not a lot of that in the air we breathe. Xenon, ammonia. And you can see that ozone is there in really small amounts, but it performs like a really vital task of reducing the amount of UV radiation that hits the Earth. And so, we need that amount of ozone there. And we'd like to have it up high in the atmosphere than rather at low in the atmosphere, because it's very dangerous to breathe in, because it's a very active gas. So this is just the last thing I wanted to check in on before we move on. Because as we've been talking about, the whole chapter is about ideal gases. And ideal gases are ones where the molecules don't interact with each other at all. And we call them ideal because they don't exist. Real gases are real molecules, and they interact with each other in real ways. And so we will see deviations from ideal behavior in the real world. And so KMT, the kinetic molecular model theory, describes the behavior of ideal gases as not having any actual volume, with no attractive and repulsive forces. And that's not true. I mean, gas particles aren't just, points of mass. They have real volume. They have real size. And they do experience attractive and repulsive forces between them. Even helium, which is about as an ideal gas as you can possibly get, will have some attractive forces together. And that's what we're going to be talking about next, actually. What are the attractive forces between molecules, and how do they affect their ideal behavior? Here we can see that most real gases deviate most at really low temperatures. And so, because at really low temperatures, gas molecules stop moving as quickly. And when they stop moving as quickly, they spend more time, or they have more of an ability to make contact with each other and stay in contact with each other. And at very high pressure, the same thing is also true. Extremely high pressure, you're basically pushing gas molecules together and forcing them to interact. And when you're forcing them to interact, they deviate from ideal behavior. So let's just have a look at some of the common gases, what an ideal gas would be, and what real gases are. So an ideal gas has a molar volume of 22.4. We sort of, that's what an ideal gas is. We can see that some, like helium, is slightly higher volume, and ammonia slightly lower, all around 22 liters. But you can see there's a real difference between 22.4 liters for a mole and 22.1. I mean, that's a clear difference. And the other thing that's fairly clear, an ideal gas basically would have a boiling point of absolute zero. It would always be a gas. And we can see helium is pretty damn close. If absolute zero is minus 273, helium's awfully close to that. And then we have hydrogen and neon. But you see, as we get to larger and larger gases, and gases that are more polar. You can see, you know, like ammonia is fairly polar. And hopefully we remember the difference between polar and nonpolar, right? Polar molecules have more electrons at one side of more electron density on one side of the molecule than the other. And so that makes it polar. And so ammonia has a lone pair of electrons on the nitrogen. So it is quite polar. And we'll talk about how that affects its interaction with each other. But you see the boiling point is much higher than it is for something like helium. And so it varies from its ideal point quite a lot. Same with chlorine, carbon monoxide. These things have much higher boiling points than helium. And how we calculate the difference is by using something called van der Waals equation. Van der Waals was a Dutch chemist back in the 19th century, I believe, and came up with a lot of like really interesting theories that are still hold today about how molecules interact with each other. And he was able to show that what a real volume of a gas particle is, and how that will affect the ideal gas laws, and what's the effect of attractions between these particles. Do they attract each other? Do they repel each other? And so we see here that an ideal, so PV equals to nRT, we know that's true. An ideal gas would act like this. An ideal pressure would be like this. But he showed that with a value of A and B, he calculated these constants for A and B. A would relate to factors that influence the attraction. And so the more they attract each other, the more they would affect the pressure. And B refers to what the actual volume of a particle is. And so if these were like really big particles, you would suspect they would affect the volume of the overall gas itself. And so this is a measure of the number of moles, the actual volume, number of moles, and how it affects the pressure and the volume. So let's just have a quick look and see how they change. So ideally would be 0 for an ideal gas would have a 0 for A and 0 for B. There would be no attraction, and the volume would just basically be 0. It'd be just a single point in space. And you see that helium is pretty close to 0 for A and 0 for B, showing that it's pretty much the most ideal gas there is. But notice A is the attractiveness. The more polar, the more ways that molecules can interact, the constant A goes up. And you can see big differences. Just look at xenon. Now, xenon's a noble gas, and xenon's not polar. Xenon is nonpolar. But look at the difference. The value for A is like over 100 times greater than it is for helium. And we'll explain why that is in the next chapter. Even though it's not polar, it does interact with itself a lot more. Chlorine, ammonia, water, much, much, much higher. Take these dogs for a walk. Much, much, much higher attraction between these molecules. And so A is much, much higher. As far as B goes, we can see that the bigger the molecule, the more the variation from ideal. Hey, guys. Thank you. You see the big change from ideal. Like for instance, xenon is much, much larger than helium. And so B, which changes the volume, is a lot greater. Same with chlorine. Chlorine's much larger. And so we get this big change in volume. So, and this just shows how, basically why that works. So at low pressure, you don't see a lot of interactions between the gas molecules because there's a much greater distance between them. When you increase the pressure to quite high, you're moving those molecules closer and closer together. And so they start to interact with each other much more than they do over here. And so at very high pressure, you're forcing these interactions together. You're going to see big variations from an ideal gas to like a real world gas. So before we leave this, are there any questions about gases or gas laws or anything we've discussed so far? So, because next I'm just basically going to jump right into intermolecular interactions.
I had a question about the van der Waals constants. What does the L stand for?
L is liters. That's just the volume.
Oh, okay.
So A is atmospheres times liters squared over moles squared. And that is just based on, because it's, here we have moles squared. Here we have volume squared. Let me get my pointer out. Here we go. Yeah, so here we have moles squared, and here we have volume squared. So the A will have volume squared and moles squared just to eliminate that because we're dealing with pressure here. Okay.
Okay, thank you.
Yep, no problem. Yeah, so remember, you don't have to memorize any of that either. If I have a question about, I'll give you the equation and the values for A and B. So I mean, try to memorize this is ridiculous. Any other questions before we move on? Okay. Let's go to the new chapter. All right. So we talked a little bit about molecular shapes. We were talking about VSEPR, and we were talking about how molecules are arranged, how the electrons around molecules are arranged, and so we would have. Excuse me. Hey. So we would have molecules with bonds and lone pairs of electrons arranged in space to take up the most distance they can between them. And so we talked about that. We talked that was VSEPR, right? That was the model where electron pairs sort of deflected each other. Man, Jerome, here, come on up here. Come on. There you go. So the space the electron pairs are repulsive. And so they would repel each other and take up as much space, avoiding each other as much as possible. Well, now we're going to talk about how those molecular shapes have real world chemical effects and how they affect both the chemical nature of them and the physical nature of them as well. Okay. So just briefly, just go over the different physical states. I think you all know what the different physical states are and how they change from different phases, change from one to another. And we talked about melting curves. Like we went over the melting curve of water when we were talking about physical chemistry, or remember the thermochemistry. And so we looked at the phase changes, the heating curve or melting curve of water. We noticed that the temperature didn't change when it was going through a phase change. When it was boiling, the temperature would stay at 100 degrees. When it was freezing or melting, it would stay at 0 degrees. So we're going to look at some of those quantitative aspects of changing from one phase to another. And then finally, the different types of intermolecular forces. And this is the key to the whole chapter. What are the different classes intermolecular forces. And when I say what's the difference between intermolecular forces and intramolecular forces? Could someone tell me? What's an intermolecular force? Super quiet. What's the difference between inter and intra?
Is it like when it's the inter is when they're working with another molecule?
That's right. And what's intra?
Like inside itself.
Exactly right. That's Kyle, right?
Yeah.
Good work. Yeah, so that was like one thing that always drive me crazy. Like, when undergraduates would always talk about intramurals. And it's like, no,
Yeah.
it isn't intramurals, it's intramurals. And every time you say that, I get confused in chemistry class. So you got to stop saying that. Yeah, so intra means inside a molecule itself. So that'd be the forces of the actual chemical bonds. The chemical bonds and the interactions between the lone pairs of electrons and the electrons and bonds, those interactions. Intermolecular forces are those attractions and repulsions that take place between separate molecules, sort of outside a molecule. And so we're going to look at the effects that those have on chemistry and their physical natures. All right. So we know what the different phases of matter are. We got gases, liquids, and solids. And if you really want to get technical, yes, if we look at the sun, we've got a different. We got also have plasma. We're not really going to be dealing with plasma. So each physical state, we call that a phase, right? Solid phase, gas phase, liquid phase. They're physically distinct, and the properties of each are balanced, really. This is where we're going to get into the different forces in between, different potential energies and the different kinetic energies. Now, the potential energies are in the form of attractive forces. Those are the forces that pull molecules together. So if they pull molecules together, that's actually a potential energy, and we can see the difference. That's when we melt water, for instance. We overcome a certain potential energy of those molecules being drawn together. When we boil water, we basically overcome all the attractive forces, all the potential energy between molecules, and then pull them apart into gases where they don't interact nearly as much. And that is actual energy that you need to overcome. That's potential energy. Now, kinetic energy, as we know, is associated with movement. Kinetics means moving. And that tends to disperse particles. Like the more energy we put in, we're reducing the potential energy between the molecules, and we're increasing the kinetic energy. And as we increase the kinetic energy, they're moving faster, it tends to move away from each other. And so there's a balance between the amount of potential energy that pulls things together and the amount of kinetic energy which tends to push things apart. So just like Kyle elaborated for us, intramolecular or bonding forces are found within a molecule. And that is chemical behavior. That is breaking and forming bonds, okay? And each phase of matter is the same in this chemical behavior. I like to point out that this is one of the biggest things that beginning chemistry students have. Like when you boil water, and you're talking about forces, they assume that when you boil water, that the forces keeping like the water molecules together break. And so then you have hydrogen and oxygen. And that just isn't true. You have water, but it's not being held together by intermolecular forces anymore. The intramolecular force inside a molecule is still there. So hydrogen stays bonded to oxygen, regardless of whether it's a solid or a liquid or a gas. Those are always going to be there. Intermolecular forces are found in between them. And that is not so much chemical as physical. And so, because the strength of those forces are different depending on whether you have solid, liquid, or a gas. So, as we've just been talking about the whole last chapter, in a gas, there's very little intermolecular force bringing molecules together, just because they're just moving so damn fast. But when they're a liquid, they have to form connections with each other, or else it wouldn't be a liquid, it would still be a gas. It's that intermolecular or sort of non-bonding forces that make them a liquid or a solid. And that is a physical change. Remember, not a chemical change. We're not breaking up chemical bonds when we go from a solid to a liquid to a gas. We're changing physical interactions and physical states between a solid, a liquid, and a gas, okay? Let's look at the kinetics of each one of these molecules. So, let me get my point here. So, with a gas, we have really, really weak attractive forces. So very, very little potential energy, lots of kinetic energy. So the particles are, I don't know why this isn't working. Oops. Don't want that. All right, so the particles are far apart. So a gas has no fixed shape and no fixed volume. Basically, what that means with a gas, no matter how much gas you put in a container, it fills the container. It seems strange to think it that way, but yeah, no matter no matter what the volume of the container is, just a little bit of gas will fill it. Basically, it fills the entire space. The pressure won't be very high, but it will fill the whole container because gas doesn't have a shape or a volume. But with a liquid, attractive forces are stronger. The particles aren't moving nearly as fast. So as the kinetic energy goes down, potential energy goes up. And so they interact with each other much more. So the properties, so a liquid doesn't have a shape, doesn't have a fixed shape, as we know, but it does have a fixed volume. So if I pour 1 liter of liquid into a 2-liter container, it's not going to fill the whole container. It's still only going to be 1 liter, but it will take whatever shape that container is. Now with a solid, the motion is basically nil. There's very, very little motion. So the particles are fixed in place and the attractiveness between them is pretty much maximized. And so now, obviously, a solid has a fixed shape and a fixed volume. So the difference is as the kinetic forces go down, the attractive forces go up, and you change the state between gases, liquids, and solids. So a gas will conform to the shape and volume of a container. And can you compress it? Certainly you can compress it, as we've shown with the gas laws. As the volume goes down, pressure goes up. And the ability to flow, well, yes. I mean, you can basically pour heavy gas out. You can actually see it, like with CO2. You can actually just pour it out of a container and fill another container with it. Or if you're like a really heavy gas, like xenon or something like that, you can like pour it out and watch it fill up a container. Now with a liquid, the compressibility is very low, like water for basically the whole hydraulics works because water doesn't compress. You can like put water under a lot of pressure and it does not change its volume. And so you can use it to, move things under very high pressure with hydraulics. The ability to flow, yes, certainly. Water flows, as we well know. And other things that are liquids, like, molasses, still a liquid. Does it flow? Well, yeah, if it's warm enough, it'll definitely flow. And then a solid, compressibility is almost zero. Although, with the, I think we talked before, about solids will expand and contract depending on temperature. And that's why there's those gaps in bridges. So when it gets warm out and they get a little bit larger, the gaps will close. And when they get a little colder, the gaps will be a little bit wider. You don't want to have you don't want to eliminate the gaps entirely, because then when it expands, that would just basically break the bridge apart. And the ability to flow, no, you don't really flow solid, as we well know. So let's talk about the phase changes and the energies involved in each one. I think we talked about this a little bit when we talked about thermochemistry. So as the temperature drops and the pressure goes up, there we go. As the pressure goes up, molecules in the gas phase come together and form a liquid. We call that condensation, right? And then the opposite process, going from a liquid to a gas, we call that vaporization. So energy going in causes vaporization. Energy coming out, we call that condensation. One is exothermic, one is endothermic. Endothermic is vaporization, because we have to put energy in to break it, to break those interactions. Condensation is actually exothermic. Energy is leaving as gas is losing energy and then becoming a liquid. Energy is released. And so liquid to solid, we call that freezing, of course, and the opposite, we call that either fusion or melting. It sounds kind of weird to call, because fusion, we think of making a solid. But we talk about the heat of fusion is the amount of heat involved when something either freezes or melts. So one is negative and one is positive. And then gas to solid, we call that sublimation. And there's a few compounds that do that. I'll show you an example in a minute. Freeze-dried foods, for instance, are made by subliming water. So they go right from a solid to a gas. So at very low temperatures, but very low pressure, you can basically remove all the liquid. The solid ice will just go directly to a gas under very low pressure, leaving the things frozen, but with the water gone. So the opposite process, you just take a gas, goes directly to a solid. We call that deposition. And you can see that sometimes when gas will freeze directly, like if it isn't cold enough to do it around here. I'm from Canada. I remember this happens quite clearly. When it gets like really cold overnight, you see like frost, for instance. A lot of frost comes from just air, the water vapor in the air freezing directly and just sort of skipping the whole liquid part entirely. And so we call that deposition. So these are the different changes in energy for each one of these processes. And again, we talked about this a little bit when we did thermochem, when we did the melting curve. So we can see that, do a little drawing here. So when you're subliming something, you're going directly from a solid to a gas, and that is positive because you're adding heat to that, you're adding energy. And so those changes absorb heat. When you're subliming or you're vaporizing, when you're going from something with low kinetic energy to high kinetic energy, it's heat that makes that change. And so you have to add that heat. Heat has to be added to that system. And so that is positive. So positive over here, those are endothermic. Now over here, these are exothermic reactions. When you're going directly from a gas down to a solid, or you're going from a gas to a liquid, or from a liquid to a solid, when you're reducing the amount of energy in a system. You're reducing the energy, and so the kinetic energy goes down. You go from a gas to a liquid, or a liquid to a solid. Those are exothermic processes with a change of energy negative, because energy is leaving. And so when the energy leaves, obviously now there's less energy, less kinetic energy than there was before. So the molecules are when they were moving quickly, are now moving more slowly, and you change the phase. So delta H for sublimation, delta H for vaporization are going to be positive. Delta H for vaporization, for freezing, or sublimation are going to be negative, because just think of it this way: is there less energy before or after that process took place? And when you think about something freezing, there's less, because you went from liquid to a solid that isn't moving at all. So there's less energy in the solid, less kinetic energy in the solid. So that had to release heat. So that would be exothermic. Any questions about so far? How the different things are either endo or exothermic? Or is everyone already thinking about what they're going to have for lunch? Okay. Yep. Pretty much. Fair enough. All right. Let us press on. So equilibrium isn't really something we have talked about a lot. Talked a little bit about it when we talked about strong acids versus weak acids. Someone give me a good indication of what, or explanation of what is an equilibrium?
Balance.
Balance is a good one. Mm-hmm. Anything else? Well, that's this question. Is equilibrium static? Does equilibrium basically mean no change? Because when I think of balance, I think things are equal or even.
Like one both products and reactants are in like have the same concentration.
Where the products and the reactants are the same concentration.
Yeah, like they're present in same, like not same, but like they're present in like a similar amount of concentration.
Okay. Oh, so they don't, the concentrations don't change. They're not the same. They just don't change.
Yeah.
Okay. That's a good one too. Anybody else?
Or what's going in and what's going out is the same. So there's the net effect is no change.
Oh man, that's a really good one. Because yeah, basically that's it right there. Yeah. So what that basically means is that most people think, a lot of people, including me, think of equilibrium as being static, as like, because it basically does mean that the concentrations of like product and reactant don't change, or in this instance, the concentrations of gas and liquid don't change, and that's, it's true, but it's not static. And that's actually something we studied when I was in San Diego at Scripps. I don't know if I may have mentioned this in class, that we worked on a virus called human cytomegalovirus. And like, gee, I wonder who's interested in viruses these days. But anyway, don't freak out. It's a virus that, like, I don't know, 3/4 of you have right now. Like, most of us have this virus. But it's not a problem. And so for years, nobody was particularly interested in it, because it didn't seem to do anything. And so, yeah, you got infected with it, but it didn't do anything, so who cares? But then HIV came along. And one of the first things that was noticed about patients who had AIDS was that they went blind. It's like, that's the weird, what the hell is that? Well, it turns out that that was cytomegalovirus infecting, that was already in your eye, infected, actually one of the places where it stays is in your retina. And because HIV destroys your immune system, once the immune system goes down, the HIV or the CMV, cytomegalovirus, goes up and basically takes over. And so what we actually determined was that there's what we call a dynamic equilibrium. Whereas what was happening is that this virus was being created constantly and being eliminated constantly. The immune system was constantly eliminating it from your body, but it was there at extremely low concentrations. But it was active. It wasn't passive. It wasn't just lying there. It was being created, but it was also being destroyed simultaneously. And the thing is true here. When we have a liquid-gas equilibrium, it doesn't mean that the gases are just staying a gas and the liquid's just staying a liquid and nothing's happening. Actually, both are occurring at the same time. The gas is turning into a liquid and the liquid is turning into a gas. But the rate at which they're doing it, as Prejean mentioned, is the same. And so we have gas molecules that are basically becoming liquid again, going down, and we have liquid molecules becoming gases. So we have both happening simultaneously. And so the vapor pressure, as we talked about the vapor pressure, we talked about the gas laws, that's the pressure exerted by the vapor on the liquid itself. So the pressure increases until equilibrium is reached. And so if I pour cold liquid into a container like this, there will be very little gas, right? Very little, because at very low temperatures, we don't have very much vapor being formed. But as the temperature goes up, the vapor pressure also goes up until an equilibrium is established, where liquid is turning into vapor and vapor is turning back into liquid at the same rate. And so the concentration of gas doesn't change. But what happens is as we increase the temperature, the vapor pressure is going to go up and up and up and up until it reaches the boiling point. And the boiling point is the point where the vapor pressure is the same as the atmospheric pressure. And we call that the boiling point, right? So the boiling point of water is at sea level anyway, is the point where the vapor pressure reaches 760 torr, or 1 atmosphere. So when the vapor pressure of water is at 1 atmosphere, it boils. And so that is the 100 degrees. But we can see that there is an equilibrium, and the rate of vaporization is going to be higher than the rate of condensation until that equilibrium takes place. And so once we're at equilibrium, vaporization and condensation take place at exactly the same rate. And so the vapor pressure does not change. It will change when we change the temperature. When the temperature goes up, our rate of vaporization goes up and our rate of condensation goes down. And so we were making more and more and more gas and eliminating more and more liquid, okay? So, and this should look kind of familiar. This was basically one of the last things we looked at in the gas laws. Remember, we have a distribution of the speeds of these different molecules based on temperature. So we can see, just like we did before, now, instead of looking at the effect of the mass, we're looking at the effect of temperature. And so as we increase the temperature, going this direction, we can see that the speed goes up. And we have more and more and more molecules going faster and faster. And so here, the average is this speed, at this first temperature, at T1, the average speed is right here. We increase the temperature, and now the average speed is right here. It's gone up. And as we increase the temperature, the average speed gets higher and higher and higher until these molecules start moving so fast they vaporize. So it's these molecules at the surface that are moving so fast that they sort of just leave the surface and become gases, okay? And this is the amount here, this is the amount of kinetic energy you need to overcome these forces here. And these are intermolecular forces. These are the forces that are holding these molecules together. So like with water, and we'll show what these different forces are. Water is being held together by, we'll see hydrogen bonding is one of the major forces with water that holds the molecules together. And you need to overcome that interaction by increasing the kinetic energy. So they move faster and faster and faster. Finally, they start moving so quickly, they break apart, vaporize, and become gas, okay? Any questions about this so far? You can see the difference between, this is why something with less intermolecular force, like butane, for instance. Butane is held together with extremely weak intermolecular forces. So it doesn't really take a whole lot of energy to break them. And so the boiling point of butane is really low compared to something like water. And really, the difference, why the difference in boiling point is so great is because the intermolecular forces with water are so much greater than they are for butane. And we'll learn about what these are. But I just wanted to, any questions about this so far? Now that I finally got the doggies a little quieter. All right. So let's look at some of these. So these are the factors affecting vapor pressure, as I just mentioned. As the temperature increases, you get more and more and more molecules moving fast enough to enter the vapor phase. And so the vapor pressure goes up as you have more and more molecules in the gas phase. Gas pressure is going to increase. So as we know this already. We have learned the higher the temperature is, the higher the pressure. Learned that already. And so the weaker those forces are between them, the less energy it takes to break those interactions and get them moving quickly. So the more easily those particles enter the vapor phase. As I just mentioned, like butane is a gas at room temperature. So those molecules are held together weakly and they move quickly. Water is held together with much more interactions. So they move much more slowly because they're stuck together. And so lower the vapor pressure. So the weaker the forces are holding these things together, also the higher the vapor pressure is going to be. Okay? Those are the main two things when we're comparing one molecule to another and trying to determine which one should have a higher vapor pressure. What are the intermolecular interactions between them, and what's the temperature? So let's look at this is just show you the different, 3 different liquids and the different intermolecular forces between them. So here we've got, and it's a plot of we've got vapor pressure going up as temperature goes up. And this will be true regardless of what we're dealing with. anything from like, helium to iron. As we increase the temperature, the vapor pressure is going to go up. It's just a matter of how quickly. And how quickly is dependent on the intermolecular forces. So we can see with water, slowly increase the vapor pressure as the water goes up until we get to atmospheric pressure at 100 degrees. So we know that, right? I mean, we know that water boils at 100. That's what that means. Now, ethanol, we know that ethanol boils at a lower temperature. That's why we can distill ethanol from water. When we boil a mixture of ethanol and water, the ethanol will boil first. And so at 78.5 degrees, basically, if we have a mixture of both of them, the ethanol boils at 78.5 degrees and leaves the water behind. That's basically, that's how we make scotch and rye and whiskey and vodka and everything else. It's that because it boils at a lower temperature, because it has less intermolecular interactions, ethanol does, than water does. It's less polar. So water would look like this, right? Ethanol looks like this. And diethyl ether looks like this. So we can see with water has oxygen here with its two lone pairs. And so it's pretty polar. Ethanol has oxygen with its two lone pairs on one end. And so it is also polar, but not as polar as water. And diethyl ether has actually the same chemistry, the same number of atoms as ethanol, but they're in a different place. And here we have oxygen in the middle rather than on one end. And so it's much less polar because it's in the middle rather than at the ends. And so we can see that ether boils at a much lower temperature. In fact, at room temperature, it has a very high vapor pressure, whereas water and ethanol, so this is room temperature down here. We see there's a huge difference. Water is very, very low pressure. Ethanol is higher. Diethyl ether is practically half of vapor pressure of the room. And so very, very high vapor pressure. And that's why ether basically, if you open up a bottle of it, the fumes just come like flying out. You don't want to be around. It gives you a really bad headache. So it's the shape of these molecules and where the oxygen is, where it is in the molecule, and what's around it affects the vapor pressure and how much it boils. So any questions about that? Everyone's really looking forward to lunch at this point. Okay, just a couple more slides and we'll go, okay? All right. So boiling point, temperature, which the vapor pressure equals the atmospheric pressure. That's why water boils at a lower temperature, high, like at the top of Mount Everest. I think water boils at around 75 degrees. The vapor pressure is so low. Boiling point of water in Death Valley is higher than 100. I think it's around 101 or 102 degrees. Just the vapor pressure. So below sea level, the vapor pressure is a little bit greater than it is at sea level. So the normal boiling point is basically whatever is observed at the standard atmospheric pressure. And so as the external pressure on a liquid increases, the boiling point increases as well. So if I increase the pressure, and that's why in a pressure cooker, the boiling point of water goes up. That's why it cooks so much faster, is that you've got liquid water in there at 400 degrees. Whereas on the stove in a pot with the cover off, it's 100 degrees C. Inside, it's much, much, much hotter. It's basically at very, very high pressure. It takes a lot more energy to get all of those water molecules to get into the vapor phase, because the pressure is so much higher. Instead of going up to 1 atmosphere, now you need to go to 2 or 3 or 4 atmospheres. So it takes much more energy to get all of that liquid into the vapor phase or the gas phase. So the boiling point goes up. That's how pressure cookers work. Here's an example of a molecule that goes directly from a gas to a solid. I think we're sort of all familiar with iodine. So here I've got iodine gas. We just heat up iodine. This purple gas here is iodine, and it goes from a solid to a gas at fairly low temperature, around 40, 50 degrees. So if you have iodine gas and you put in, this is just a tube with some ice in it. And so it goes directly from a vapor to a solid. And you get these like really, really beautiful dark purple crystals. But when we buy iodine in drugstore, it comes in a liquid. It's like, why is it a liquid? Well, because then it's dissolved in ethanol. That's what you're buying, is iodine dissolved in ethanol, and that's called a tincture. Tincture of iodine is solid iodine dissolved in a liquid solvent. Okay. So intermolecular forces, again, they attract molecules together. And so they have either partial charges, or either polar with some partial charges, or they're ionic. So we would expect ionic ions to have really strong interactions, and they do. And molecules with either a partial charge or some sort of induced charge. We'll talk about how the charges get induced next class. And they're relatively weak compared to bonding forces because they involve much smaller charges and they're much further apart. When two atoms are bonded to each other, they have to come in very close contact in order for that to happen. Individual molecules are much further apart than atoms in a molecule. So I'm going to. So here I'm just going to do just a really quick comparison of the bonding forces we're talking about and the non-bonding forces we're talking about. We'll leave it there. So these, we're sort of familiar with these, right? These are like these are the basic kinds of bonds we know can form. Learned this early on, a long time ago. So we've got ionic bonds, and we know that's we have two charged atoms. We have an anion, we have a cation, and they don't necessarily can be atoms. We know we have polyatomic ions as well. Something has lost an electron, something that's gained an electron. They come together due to electrostatic interactions, and it's a fairly high energy bond. They are held together. This is the amount of energy you need to break them. So they're very, very, remember, something like salt, we talked about, like you need to add a ton of energy to get salt to melt, like thousands of degrees in some instances. Covalent interactions, now those electrons are shared. And so we have nuclei and shared pairs in between them. And energy for covalent bonds is less, but still quite high. And An example would be just like, any sort of covalent bond, hydrogen atoms, oxygen atoms, N2, triple bonds. Those are all covalent bonds. And then we talked about metallic bonds, not quite as much. We talked about metallic bonds. And the difference here is that these are all cations, and the electrons is basically, we have to remember the sea of electrons. They sort of just flow all around them. And so the energy of these are around the same basically as for covalent bonds. And just basically any metal forms these metallic bonds. Now, when we look at between non-bonding force, these are forces between molecules. I'll just quickly go through these. We'll come back to them next week. These are the different forces. So we have strong forces, and the first one are ion dipole forces. So if you sort of remember what a dipole is, a dipole is where you don't have a full charge, but you have you have more electron density on one side of the molecule than you do on the other. Like, so for instance, like with water, let's say this is water. So this interaction would be between an ion, like a salt, like we would have sodium ions in water. So in salt water, seawater, this would be the interaction between them. So water we know is a dipole because it has more electron density near the oxygen side, and it would bond with the sodium. And so this is an example right here, that I should have noticed. This is the sodium water bond. So that's quite strong. That's almost as strong as a covalent bond in some instances. Next is the hydrogen bond, and the hydrogen bond is probably the most important. If any of you are becoming biochemists, and I hope some of you do, the hydrogen bond is probably the most important biological bond there is. And this is, we have a polar bond between a dipole and here's our water molecule. And so it's basically bonded with something with high electronegativity like oxygen or nitrogen or fluorine. So this is a pretty strong bond, but you can see not nearly as strong as ion dipole, like, 4 to 50 times, 4 to like 20 times less. Next would be dipole-dipole interactions, where I have two different dipoles. So here I've got iodine chlorine. Chlorine's a little more electronegative, so it has a little more of the electron density. It's a dipole. It interacts with another molecule because iodine has a little less electron density, so it's partially positive. So you have a partially positive and a partially negative side interacting with each other. Next, you have an ion-induced dipole. So in this instance, I have an ion here bonding with something that isn't a dipole. But because the ion is charged, it actually induces a dipole. So what does that mean? So that means if I have something with a charge on it, like iron, or something with a high positive or negative charge, it basically will either pull electrons to itself or push electrons away from itself if it's negative. And as it does that, it induces a small dipole on something that usually doesn't have a dipole. And so it basically, what it does, it polarizes that other molecule. It forces it to become slightly dipole-like. And so that is pretty weak. And then next, we have one dipole inducing another molecule that isn't polar into becoming slightly polar. That's even weaker. And then finally, we call them dispersion forces or London dispersion forces. Basically, you have something that isn't a dipole and another thing that isn't a dipole. And just the fact that they push themselves together induces a very small dipole, really, really small. And you can see that this interaction is really small. That is the lowest of any of them. And it's basically the interaction of last resort. It's the interaction that any molecule can do. Even helium can be forced at some small level to make tiny, tiny dipoles, not very strong. And so if there's nothing else molecules can do, they can always do that. And so it's extremely, extremely small. So I'm going to leave it there. Any questions about these particular forces? I'm going to come back to this next week. So, but I just wanted to sort of introduce you to the different forces and how they're stronger or weaker than each other. Any questions? Anyone left? Everyone's gone off. Any questions from folks before we go? I'll see some of you at quarter after. Any questions about the test? Maybe.
Is it hard?
I've only written a couple of questions. I mean, let's face it, it is going to be more difficult than a typical test because you've got all day to do it. And
So, I was going to ask if it's going to be the same way. It's going to run the same way, like the last exam.
yeah, I'm going to release it. I'm going to release it at like at 10 in the morning, and then you'll have 24 hours to finish it.
Gotcha.
Is
Okay.
it the same length and everything, like multiple choice and some written questions?
Yeah. I mean, yeah, about the same. Yeah, but remember the last one was a little longer. Of course, the first lecture test you did, you actually sat down and did it, right?
Mm-hmm.
I think this one probably be a little longer because you got more. You can't say you're going to run at a time when you got all day.
Is there still going to be a class that day?
No.
Okay.
No class, no labs. I don't want you guys to freak out. We got enough things to freak out about.
How many questions are there going to be?
Don't know. Haven't decided.
Understandable.
Yeah, I mean, like I said, I've only got a few questions done. I'm looking around at some good head scratchers. All right. So yeah, so I have an announcement there about the different things that are going to be on it. Nothing here. We haven't anything we talked about today will not be on the test. So you don't have to worry about diffusion and the gas laws. You don't have to worry about the intermolecular forces. There won't be any of that. But solutions, solution chemistry, solution reactions, thermochemistry, and gas laws. Those are the three big things. Okay? I'll see you this afternoon. Stay well, everyone.